Welcome to the PGRO and Syngenta Roadshow. My name's Leah Howells. I'm a data scientist at PGRO. And today I'm going to talk a little bit about the project that I've been working on for the past 3.5 years at PGRO, involving the forecasting of maturity and yield in vining peas. And I'll talk a bit about the exciting development that's going to happen over the next few months in terms of a platform to host the model, which will allow people to access them, and also how we can possibly expand the models into other crops beyond vining peas, so other pulse crops and non-pulse crops as well. So just to introduce the project, it started off in 2019 as an Innovate UK knowledge transfer partnership between PGRO and the University of Nottingham. And it's since evolved into another Innovate UK project, but this time it's a SMART project. And it's scheduled to go on until 2024. So the main aim here, or the main background to this, is that the prediction of vining pea yield and harvest dates is very difficult. They're a tender vegetable crop, which means they have a very narrow window of opportunity for harvesting that's around 1 day. And so timeliness is key when we're trying to harvest the crop at optimal maturity and making sure the quality's there. Currently, there's a heavy reliance on the use of accumulated heat units, also known as thermal time, to predict harvest date. And when we're talking about sampling for tenderometer readings to make sure that we have the correct quality, it requires in-person sampling and often quite a lot of it. For yield prediction, there's no current standard method for predicting yield, but you can estimate it using things like biomass sampling or pod counts, node counts, plant counts, things like that in the field. But again, that requires in-person sampling. And so it can be quite labor intensive. And when you've got quite a large growing area, you can spend a lot of time sampling. And so the objective of the project is the development of a forecasting system for vining pea maturity and yield, with a novel focus on machine learning and remote sensing. So you may have seen something like this before. This shows how temperatures have changed since records began up until the present day. As you can see, that the 5 warmest years, we actually have 2022 now, should be added to this, have been in the last decade or so. And so these hot weather events are not only becoming more frequent, but also more intense as well. So temperatures are becoming higher, and temperature records are being beaten more frequently. You may have also seen something like this. This is a satellite image that was taken during the heat wave in 2022 in July. You will be well familiar with the effects of that at ground level, but this is just a different perspective. As you can see, the right-hand side, sort of the eastern seaboard of the UK and the south, all the way up from to Scotland and all the way down to Kent, suffered the worst of the drought and the heat wave. So this is just to emphasise that in the east and the south, these are the areas that are going to suffer most in terms of increasing temperatures into the future with climate change. And so these are the areas in particular where resilience from the effects of climate change are becoming most important. So I did an analysis of trials data, PGRO vining pea trials, between 1985 and 2021. And as you can see here, that the number of growing days, that's days between sowing and harvest at tenderometer reading 100, so first harvest, of the main standard variety has decreased over that time, and it's decreased by 3 weeks. And the main reason for that is because of increasing temperatures. At the same time, if we look at the number of accumulated heat units that have built up in that time, so between sowing and harvest, you can see that that number has also decreased. And essentially it's because we're getting days sort of shaved off at the harvest end of the season. And with every day that you lose opportunities for those heat units to build up. So they're just not building up in time. Traditionally, with vining peas, you would use a target value. So here you see this horizontal line of about just under 700 heat units. And when you reach that, or you forecasted to reach that value, you know that that's when you're going to harvest. But as time goes on, the likelihood that we're actually going to reach that value has decreased, and it continues to decrease. So we could adjust that value down and reduce the target value, but with the way things are going, you would just have to adjust that again in a few years. And so what this says is that we need another forecasting method that doesn't just incorporate heat units, but incorporates all the other factors which affect pea growth as well, to make something more robust and flexible that can be used well into the future. So at PGRO here, we've come up with a machine learning model, or two models, one for harvest date and one for yield, to predict their respective variables. So what is machine learning? Well, a machine learning model is essentially an algorithm. So you put in data, it does a series of complex calculations, and it sort of pops out a forecast on the other end. And you can use this and the relationships that it insinuates between variables to then forecast future data. So things that haven't happened yet, you can then make assumptions about the way a crop is growing, and things like harvest day and yield. So the beauty of machine learning is that they can incorporate a huge amount of many interacting factors, ultimately making very, very complex problems. So rather than assuming or estimating harvest day, for example, with just heat units, that would be a very simple relationship. You could put in all sorts of variables that aren't just temperature. And the interactions between the variables and also the variables and the thing you're trying to predict may not necessarily be linear by themselves. So this isn't a process-based or physiological model, which traditionally would model the way a plant is expected to grow. These machine learning models essentially model what is actually happening in the field, and then from that, you can get a more accurate result. So the question here was, can we model crop development to minimize the requirement for sampling in the field of these vining pea crops? So if you imagine the growing season of a vining pea crop, like a timeline from drilling to harvest, at the end, you have a kind of a sampling window. So there's no fixed start date here, but in the few weeks running up to harvest, you would take tenderometers readings, samples from each field, and you could have upwards of 8 samples on individual days in the run up to harvest. And that's to ensure that you're harvesting at the exact quality that you want. But of course, the amount of labor here, the amount of field visits, it all adds up. So what if we could model an earliest estimated sampling date and say there's no need to take any samples before this point, and this could potentially halve the number of samples that need to be taken. So with our machine learning models, of course, there's lots of complex variables that go into them. So let's take a look now at the ingredients, essentially, of these models. So one of the main ones, and that's how the way that we get crop-specific estimations, is the use of crop data. So for each field that we want to estimate, we have a drilling date and a date of full flowering, which I'll talk about in a minute, the variety that was drilled in that field, the target tenderometer reading that we're after. And then we have spatial data, so the coordinates of the location of the field, which influences things like elevation, proximity to coastline, things like that, and the soil properties. And then we have Canopy Reflectance data. So as I mentioned before, this project has a novel use of remote sensing data. So this Canopy Reflectance data is not collected in the field, but it's collected by satellites. And I'll talk about that in a minute. And finally, arguably the most important thing that affects the crops is the weather. So temperature, precipitation, and solar radiation. And all of these variables go into the models and give an estimation. So in terms of training the models, this project has used commercial crop data for over 17,000 individual crops for the last 21 years. So between 2001 and 2022. And then because this is a future forecasting system, the model's updated annually to incorporate the previous season's data. So it's always up to date and it can always cope with rapid changes in climate, things like that. So Canopy Reflectance, that's one of the ingredients in the models. So it can be very, very useful for sort of serves as a snapshot of what the crop is doing at any given time. So as you can see here, we have a series of images that were taken by the Sentinel-2 satellite of this crop. And as you can see, it gets greener as we go through the season. And there are lots of other non-visible wavelengths that are reflected by crops as well, at different growth stages and different stages of canopy closure. And you can insinuate things like crop health, things like yellowing, as well as water content and potential yield, because different structures of the crop reflect things differently. So pigments reflect different wave bands. So I'm talking about things like near infrared, red edge, and shortwave infrared radiation, as well as the red, green, blue visible light that we see. Things like the flower structures of the crop, and again, any yellowing or lack of chlorophyll, you'll be able to pick those up as well. And all of these come together to give an indication of crop health, stage of development, and importantly, yield potential. Pulse crops lend themselves very, very well to collecting multispectral reflectance data because they have a large above ground canopy, particularly things like beans, very, very tall. Because unlike vining peas, when you have a dry sort of combining crop, you have an extended season past that point of maturity, all the way to senescence. So essentially have lots of opportunities for data collection to build up a really nice picture of what the crop's been doing. And this data can be collected via handheld sensors, by tractor-mounted sensors, by drones, or by satellites. And that's what this project uses. So in order to benefit from the ability to collect lots of bulk data and process data for lots and lots of fields in one go, we're using the Sentinel-2 satellite. So this satellite belongs to it's part of a European Space Agency's Copernicus program. So there's satellite flyovers in the UK every 2 to 3 days. So over the course of a crop growth season, from drilling to harvest, you would get at least sort of 10 or so images that are usable. Because it's satellite data, of course, if it's cloudy, you don't get an image that's usable. But as I said, you do get enough over the course of the season. And it collects not only photographic true color images, but also that non-visible reflectance data that I talked about. So the data is collected at a 10-meter resolution. So although it wouldn't be suitable for something like trials, where you have individual plots of only a few meters, for field scale prediction, it's more than suitable. And of course, the data is very, very low cost. And so you don't have to pay someone to fly a drone over your land and collect data that's very, very high resolution, because it's just not needed here. So the other important thing that goes into the models is climate data. So for this project, we have a sort of network of weather station coordinate points based on the Ordnance Survey 20-kilometre grid. And so every 20 kilometres in a grid pattern, there is a point. And for every one of those points, we have a set of historic data for the weather. And then it's also updated every day for each of those points. So we have an up-to-the-minute indication of what the weather's been doing. And this data is derived from a service called Open Weather, which itself gets its data from Met Office data. And so it's good quality data. So when the models are used in real time, all the recorded data, the observations up to that point are used, and then the forecasts are generated. We have a 5-day forecast from Open Weather, and then anything beyond 5 days ahead are a historic average. So in terms of model performance, this is the harvest date model. So when we plot the observed harvest dates that was present in the actual data against what was predicted by the models, you can see we have a good agreement between observed and predicted. The R squared is 0.99, which means that 99% of variation in harvest date is able to be predicted by the model. And that translates to a mean absolute error of around a day. When we rank the variables that go into the model, so as I said, all those variables, all those ingredients that go in, if we rank them in terms of importance, we have things like variety, or we have your weather data, location data, things like that. And then the variable that comes out on top that's crucial is full flowering date. So full flowering date is has been shown time and time again to be the most informative for forecasting peak crops. So in this project, we refer to full flowering as the date on which every plant has at least one open flower. It's also known as score 6 within the industry. And that's around BBCH growth stage 61. So in terms of the yield model, we have a similar story here. When we look at the agreement between the observed actual data and what is predicted by the model, we see that the model is able to predict or explain 69% of the variation that we see in yield, which translates to a mean absolute error of around 15%. So if we rank again the variables in terms of variable importance, that location data, the weather data, the tenderometer reading, and the variety are all very important. But the most important variables are that multispectral reflectance data. So they really give a snapshot of what the crop is doing at any particular day. So rather than modelling what we think is happening or should be happening under ideal conditions, it's essentially a photograph in time of what that crop actually looks like. So here's the exciting development. So PGRO aims to expand the services it offers. And so these models are going to become available as a web app, available to use by processing growers for crop forecasting. So you will have access to the models online, and you can use them as a management tool throughout the season and access them daily to generate as many predictions as necessary. So I just inputting 6 very simple input variables. So you will have to have a field ID for each field, just to identify exactly which one we're talking about, the variety that's drilled in that field, the maturity index of that variety, the date that the crop was drilled, the date of full flower that I mentioned, that's very important, and the target tenderometer reading. As well as this, if we provide crop boundaries, so that sort of acts as the spatial data that allows the satellite data to be downloaded, and then the models take care of everything else. So here's a screenshot of the platform as it stands. So you would put in your crop boundaries here, and then it's mapped to show you that they look good, they're all correct and in the right place. And then you would upload those 6 variables in spreadsheet format and submit it. And you will receive a spreadsheet containing predictions. So you can see here's the data that was uploaded, but there's a harvest date column that's been added, a yield column that's been added, and then an overall tonnage. And that's based on the yield and the number of hectares of that field. And that's downloadable as a CSV spreadsheet. And as I said, you can go back every single day and redo it to get an up-to-date prediction. So as well as that, there's sort of visual data analysis. So if you were using this actually in the season, you would get an estimation of the next 5 days. So how many hectares are coming up over the next 5 days, and then the tonnage that goes along with that, a visual representation of tonnage or hectares over the course of the season. And so any peaks and troughs in terms of production can be seen well ahead of time. And so it's possible to go in and maybe harvest a few more crops a day early, just to avoid a large peak and keep factory production sort of smooth it out a bit and keep everything running efficiently. And you also have summary statistics here, like earliest forecasted harvest date and your average yield. And finally, another sort of feature of the app. So not only is the multispectral data included to forecast yields, but also it will enable you to have access to colour images of any crops. So here you would just select the fields that you want to look at, the date of the image that you want to look at, and it collects the images straight from Sentinel Hub. And so you can see here, and you can see that 10 meter resolution is definitely sufficient to see field sort of features. You see areas of yellowing. Often your headlands are more yellow, they're more mature than the rest of the crop. Areas of damage, areas of foot rot, things like that. So if you sort of want to keep an eye on a crop, but from a different perspective almost, this is a great example of a solution to that. So ultimately, the tool will allow you to make greater sort of decisions with greater certainty, further in advance than is currently possible. So those harvest dates and yields, you can generate predictions from full flowering onwards, because that's one of the crucial inputs into the models. But we have a limited test launch in February, in a couple of weeks' time, in February 2023, and that's a section of processors and grower groups will be given access to the model to test it during the 2023 season, see how it works, see what features they would like to possibly add, and ultimately test it for accuracy. And then we will officially launch the app in springtime 2024, ready for that 2024 vining season and beyond. So quickly, just to sum up here about the future of yield prediction in pulse crops. So the model as it stands is for vining peas, but the nature of machine learning means that the model can adapt to any data. So any crop you put in, if you have sufficient data, you could generate a prediction. So there's huge potential here for use in other legumes and non-legume crops. As I said, in terms of multispectral data, pulse crops lend themselves very, very well to this. And there's a wealth of data out there that can be added to the models, sort of crop-specific data, like things like drilling dates, yields, things like that. The accuracy of the models is dependent on the accessibility and volume of that historic data. But this is an avenue for further research. So I'm excited to see where it goes. PGRO is very much committed to expanding the models past vining peas because there's such potential, and the value of advanced yield prediction in these crops is enormous. So thank you to everyone who's been involved with the project. So PGRO, the University of Nottingham, and there's grower groups who are cooperating and providing data, and also who will be testing the models in 2023. So if you have any questions or suggestions, or would just like to know more about the project or anything relating to the project, I can be found contacted at leah@pgro.org. But thank you for listening.